Syzygy, episode 107, biggest bang ever.
Again?
And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and I am sitting, as usual, at the round desk in the office of Dr. Emily Brunsden here at the University of York. Emily, how are you doing?
Hello. I am doing very well, thank you.
Good. Listen, do we have any follow-up of anything from the last little while that we need to catch up on, or are we just jumping straight into this one?
Don't think anything else has crashed into the moon that I've missed.
No, I don't think so either. So today, we're just going to jump straight in. But interestingly, today we're talking about something which is really, really, really big. And this is becoming a bit of a theme in recent episodes, because it wasn't long ago that we were talking about the biggest black hole evs. What episode was that? I can't remember. It was a couple of episodes ago.
Yeah, 104.
This stonkingly huge black hole, which was bigger than all the other black holes, we think, at least is on the upper boundary of how big a black hole could conceivably get in the lifespan of the universe so far. So that was kind of cool. And we're following it up today with something else in the news, which was really, really big. Emily, what's going on? What are we talking about today?
So my title, in my notebook at least so far, this may or may not end up being the episode title, is Biggest Explosion Ever.
Biggest explosion. That rings a vague bell.
Yeah, so it's version 2.
Version 2. When did we we previously talked about biggest explosion ever?
We have done version 1, which was episode number 61.
Right. That's gone back a couple of years now.
Yeah, I don't even remember when that was.
No.
It was a time ago.
I mean, look, it doesn't matter because it's no longer the biggest explosion ever. But I guess if you are going to do a story about the biggest X, you've got to assume that at some point a bigger X might come along. Unless you have literally discovered the biggest possible X for which that black hole might be. It may be that there's no other black hole that could be bigger than that. But any other time that you've got, this is the record, this is the current record, that could be broken at any time. And here we are, episode 61. We're now up to an even bigger explosion, which is kind of cool.
Or is it? Oh.
Well, if it's not, we don't have much of an episode. What are you talking about?
Well, we've still got a big explosion. Let's not quibble about that.
All right. So we have a title, which is Biggest Evs, especially since episode 61 of this podcast. Brackets, or is it end brackets? Emily, look. Who's doing this? Let's get some names on this basket of bizarreness.
Yeah, so this is a paper that came out about the middle of last month, so middle of April, from Wiseman et al. And what they have found and put together from the available evidence is basically there was what they call fireball in the print media, about 100 times the size of the solar system, that has gone up and basically caused this enormous giant flare event. So
right. Sorry, hang on a sec. 100 times the size of the solar system?
Yeah. So that's a fireball. Fireball, yeah. Okay. Fireball's an interesting choice of word, but yeah.
Well, I mean, look, if you're going to explain, if you're going to write about this in the media, then you need to sort of, what do explosions look like? Well, they're just huge fireballs, right? So, what we're talking about is a massive eruption of energy, presumably. So fine, let's, for shorthand, call that a fireball.
Big, bright explosion has happened. Yeah.
Boom. And it's 100 times the size of the solar system, which is big by anyone's stretch of the imagination.
Yep.
Okay, cool. Where?
Well,
not anywhere nearby, I hope.
No. This is a very long way away. So far away that we actually have a lot of trouble detecting.
Okay.
But nonetheless, yeah. So if you kind of turn this into, I guess, some other numbers that you might want to think about in terms of how big, how bright this thing is, it's pretty. I mean, we don't use this term lightly, astronomical.
Right. I mean, when the astronomers are going, that's big, then you know that we're really onto something.
Yeah. So we're looking at 2 trillion times brighter than the sun.
That seems like quite a lot. I mean, trillion is a big number.
Trillion's not a number we actually bandy around a lot. We work with big numbers.
Yeah.
Millions, billions, we do a lot.
Trillions don't come up terribly often.
No.
So 2 trillion times brighter than the sun. Okay, so how does that compare to other really big, bright, explosion-y things? Because we've had a few of those. Like we've talked about novas, which is fairly small. We talked about supernovas. We've talked about, wasn't there like an ultranova or something? Hypernovas.
Yeah.
We've talked about like black holes doing ludicrous things. So how big is this?
Well, now in contrast to, I think, the previous episode, I'm going to be working in this episode in a unit called ergs.
Ergs, right? Okay.
I think so going last back to time I did it in joules, and for unknown reasons, I've switched to ergs.
Okay. Can we at least get a translation between joules and ergs? What is an erg?
An erg, well, if you want to know the amount of energy, it's a unit of energy, so how much energy you have. One erg, as I found one nice description, is about one housefly doing a press-up with one leg.
Right. Okay. Well, there's a mental image for you. So hang on. A joule is the amount of energy. Do I remember this right? Joule is the amount of energy that raises an amount of water by an amount of temperature. A gram of water by 1 degrees centigrade, Celsius, right?
Well, so Kelvin's the same.
Kelvin, this is all the same, but not Fahrenheit, different. So that's a joule, is you imagine a small amount of water and we raise its temperature by 1 degree. So that you get a grip on that. I don't really know how to translate that to houseflies doing push-ups. So I imagine the erg is significantly smaller than a joule.
I think it's a couple of orders of magnitude smaller.
Am I allowed to just do a quick look up?
Yeah.
Erg unit. The centimetre gram second unit of energy of work.
Yeah, horrible chemists.
Can we just please?
It's chemists.
10 to the minus 7 joules. There you go. It's a tenth of a millionth of a joule. 1/10 millionth of a joule. Yeah. Right, there we are. Okay, so now we know. It's really small. It's a housefly doing a press-up on one leg.
Yeah.
Which is like, nice work, housefly. But then again, on those scales, ants can carry, 400 times their own weight or something. So, all bets are off. But sure.
Yeah, I mean, it's actually a fairly useless unit because obviously we're going to be talking about really lots of energy.
Yeah, so why did you change from joules to ergs? Surely that's going the wrong way, or is it just to make it sound more impressive?
Well, that's what they started off with in the paper, and I thought, let's roll with it.
Okay. All right, look, we'll go with it. But regardless, it's going to be really big numbers.
We're going to talk about a lot of very, very large numbers.
Knock me out.
So 1.5, that bit's not so bad.
Sure.
Times 10 to the 53 ergs.
Okay, look, I don't care how big or small an erg is compared to a joule. Anytime you've got 10 to the power of 53, that's off the charts. That's an insane amount of energy.
So that's a 1 and a 5 and 52 zeros.
Yeah. I mean, even in joules, that would still be 45 zeros. That's a lot of zeros, Emily.
Yeah. These numbers are going to become meaningless.
Okay.
But
so for those of you who aren't comfortable with scientific notation or can't wrap your head around anything of that magnitude, let's just park it as this is big. So we need at some point to ask the question, what the hell happened? What's going on here?
Well, as we'll come to, the most logical conclusion of the event that caused this amount of energy to be released is that some galaxy that we haven't directly seen, but some galaxy has a supermassive black hole in its center. We think that supermassive black hole is on the large-ish size of supermassive black holes.
Yep.
By that, I mean, so our Milky Way is about 4 million times the mass of the sun.
As in the black hole is.
Yep, the black hole is, supermassive black hole at the center. So our one's about 4 million times the mass of the sun. The one that we talked about a couple of weeks ago was 33 billion times the mass of the sun. So,
which is a lot more.
Really big. This one's probably somewhere around maybe up to 1 billion times the mass of the sun. Okay,
so it's bigger than the one in the Milky Way, but it's considerably smaller than the really, really, really stupidly big ones. Yeah, okay. But regardless, we know that big black holes can do big stuff.
Yes. So we know that all of our explanations basically tie into this black hole because that's the only kind of astronomical object that you can get that has enough gravitational energy, it has enough sort of just awesome amount of physics going on with it to be able to produce these ridiculously huge energies that we see.
Yeah, I mean, I'm guessing, it makes sense, right, that if astronomers see, that was big, you're immediately thinking, what kind of systems just inherently have that amount of energy hanging around that could be very quickly thrown out there into the universe? And it's got to be big and it's got to be energetic because otherwise it's not going to come from anywhere.
Exactly.
Right? You've got to be able to account for it in order to then fling it off into space. So that limits the sort of systems that we're talking about to a very small subset.
Yeah, so top of your list is these supermassive black holes.
Sure.
They're the number one.
Sure. They're usually to blame, aren't they?
Exactly, yeah. So we have this object. It's about 8 billion light years away, so it's all good. Whatever happens with its explosion,
we don't need to worry about this.
We're going to be fine.
Good.
Yeah. Even if it does take 8 billion years to get to us, we're not going to care.
We're okay. And did you say a minute ago it's in a galaxy? We assume because we don't know.
Yes. Well, we haven't seen supermassive black holes that aren't in galaxies.
Sure.
So if we're going to say that that's the culprit, then we assume there's the rest of the galaxy exists.
But I guess the point is we're not looking at a galaxy and going, that one there. We've just seen the big boom.
We've seen the flash, basically.
Right.
Yeah. And we're saying, well, there probably is a galaxy there. We can at least place some limits on it, given the fact that we can't see it.
Yeah.
But yeah, we assume that it's
as opposed to, Andromeda. And it's like, oh, that's in Andromeda. We know where that is. We've just seen the flash.
Yeah.
Right.
Really far away flash. So this event, AT 2021 LWX, big supermassive black hole. And the best explanation for it is that there was a giant molecular cloud. So we've talked about these before. These are kind of, when they're not around black holes, when they're in their nice kind of spiral arms of galaxies, these are the kinds of clouds that can collapse and form new stars. But in this case, giant molecular cloud seems to have been eaten by the black hole.
Right. And that's the sort of thing when stuff is falling into big black holes, enormous amount of energy erupts out because of all of the weird stuff that happens around the edge of the black hole and all the big nasty
huge amounts of energy are
stuff.
Released. Yeah. So we need a fairly large cloud. I do have the mass written down here somewhere, but it's evading me right this second, but fairly large one. And it's not just, so when we talk about energy, right, there's when you have a flash or an explosion, a very bright thing can deal to you a lot of energy in a short amount of time. Or you can have events that happen that produce a lot of energy but over a longer period of time, and though the instantaneous energy might not be as much or it might not be as bright, because it happens over a long period of time, the sum total energy can be much bigger. Right.
Yeah, I mean, that makes sense. You can have a big flash and then it's all over and all of that energy released at once, or you spread it out over time. Big amount of energy, but it's not as bright immediately.
So that's going to become important when we talk about energy.
All right.
Yeah. But to give you, we've got lots of sort of senses of scales. This event seems to have lasted for about 3 years.
Okay.
Now.
Is that a long time astronomically?
It's a long time for a very bright, energetic event.
It does kind of feel like a long time for a really big explosion.
Yes, yeah. So this is when we get something that's basically something about 10 times brighter than a supernova, but a supernova flashes up and then decays. So it rises to peak brightness over a few days, and then it decays, gets dimmer and dimmer and dimmer over the course of a few weeks.
Right, okay. And this is couple of years, several years.
So that's a supernova, yeah. So this is 10 times brighter than that,
yeah,
but happening over 3 years or so far. Yeah.
So no wonder astronomers are looking at it and going, oh, this is interesting.
Yes.
That's not what you see every day.
And so that's where we get this largest amount of energy in the sense that it's coming from over the 3-year period. It's going to put out something like this 1.5 times 10 to the 53 ergs.
Right, that makes sense because an energy, a quantity of energy is, you can think of it as, we can hold it in a bucket. Here it is. Here's the energy, but this is energy over time. This is stuff that is happening over time, and so this is an incredibly bright thing, but it continues to be incredibly bright. There's a process happening here, which is kind of ludicrous by the sound of it. Yeah,
but then this 10 to the 53 might not be the biggest number we're going to talk about today.
Okay.
There are bigger numbers when we talk about energies. Mm-hmm. So I think it might be quite interesting to kind of build up to those numbers and put this in some sort of context.
Okay, because it's really easy to say, "Ooh, this is really big. Here's a really, really big number," and end of story, and we're done here, and we walk away and pat ourselves on the back. But we like to, we pride ourselves on the context.
Yes.
On this show.
Well, we need it to be able to talk about how this is bright compared to other bright things, right?
Sure.
So I started doing some good old Googling, getting on. Now my search history is going to be a little bit dicey from now on, and I'm not surprised if I'm going to be watched because I started, asking the search engines for things like, what was the biggest explosion ever?
Oh, good. Yeah.
What is the biggest nuclear weapon that we've ever made?
Fantastic. You're going to get a knock on the door very soon.
I thought I might.
From some people in dark suits and glasses.
Yeah. But let's go with it, right? So we have our fly doing a press up. That's 1 erg.
Sure. And that's not a lot. To be clear, that's not a big explosion.
No, it's very small. We have the biggest explosion that's non-nuclear in the world that we understand to have happened was something called ship in Halifax, Canada.
Oh, I remember hearing about this.
This was a ship that was packed full of explosives that caught fire and just went kaboom.
Yes. A lot of explosives in a very small space. And that wasn't good.
No, 1917.
Yeah. I don't remember it, but I remember reading about it, is what I'm saying. I'm not that old.
No, not yet. So that released something like 1.2 times 10 to the 20 ergs.
Okay, so that puts us on a scale here. An erg is very, very small. 10 to the 20 ergs is a boatload of regular explosives.
Yeah,
there you go.
TNT kind of thing. Yeah. Now, it's important to remember, just a side point, that 10 to the 20 is not half of 10 to the 40.
No, it's not. It's not. It's 10 to the 20 times smaller than 10 to the 40. That's yes.
So just hold that in your mind. These are power laws. So you have to, each step is 100 or 10 times each step, right? You're adding on to here. Right. So that's our boat full of explosives, the biggest explosion that we have that's non-nuclear. Of course, the biggest nuclear explosion, we have to go down that road. Something called the Tsar bomb.
Yeah,
which is a H
bomb. That was the Russian hydrogen bomb.
Yeah, Soviet Union, 1961.
Because the normal nuclear weapons just weren't destructive enough. Let's try to make one as big as we could possibly make.
It's human nature, isn't it? We're going to do it at some point. What's the biggest we can do? 50 megatons of TNT in sort of normal human speak, or 2 times 10 to the 24 ergs.
Okay, so that's 10,000 of those boats.
Yes.
Yeah.
10,000
boats filled with dynamite, filled with normal explosive going off in this one bomb. It's a lot.
It's a big bomb.
Yep. To which astronomy says, hold my beer.
Yes, indeed. Now, another sort of favourite energy measure. Now we can move to astronomical objects.
Good. Let's leave behind human destructiveness.
Yeah. Lifetime energy output of the sun.
Lifetime. How long are we talking here? The
so
sun's
10
around for
billion years or
so. So add up all of the energy that the nuclear engines in the sun are spitting out over that many years. 10 billion, you said?
Yep.
I'd expect that to be a lot. Sounds like a lot.
It is a lot.
Yeah.
I mean, we're not going to lie here.
Yeah, sure.
That's looking around about 10 to the 51.
10 to the 51. So we're jumping from the 10 to the 20s to 10 to the 51.
Yeah,
10
I didn't
to the 30s.
go finding anything in between.
That's a lot. That's a million times more. Yeah.
Or if you're still holding our 1.5 times 10 to the 53 in your head, that's something like 100th of the explosion that's just gone off.
Right. So we're talking 100 times the sun over its entire lifetime.
Has gone off in this 3 years.
In the space of 3 years. That's a lot.
Yeah.
That's quite a lot.
So, but we know the sun's an average kind of star.
Sure.
And
yep.
It's just, an average kind of energy output. So let's go to big things. My instant thought of other big explosions in the universe would be to go to our favourite black hole mergers. We've talked a lot about those with LIGO detection. So these are 2 black holes that merge together, put off a stupid amount of energy and, of course, gravitational waves as well.
Yeah, because the thing about gravitational waves, as has come up a few times, is in order to see them at all, if you've got any hope of seeing them, you need the biggest damn explosions in the universe that you can find. And that so far has been things like 2 black holes orbiting each other and eventually merging. And that event gives off these sort of space-time quakes that we can detect. But, you need something of that size. And is like that, they're really big, right? Those are very large, sudden emissions of energy.
Yes. So a LIGO black hole merger, you're looking at something like 10 to the 54 ergs.
Okay, so that's another step up from this one that we're talking about today. So it's not the biggest.
No.
So why are we talking about this? What's going on?
Wow. So a black hole merger, 10 to the 54 ergs. Let's carry on down the track.
Let's keep going.
We'll return to the question.
Okay, put a pin in that because we've just taken over the whole point of this episode, which is this is the biggest explosion we've ever seen, and we've just said, no, it's not, clearly. So we'll come back to that. Keep going.
Yep. Next up the scale, the biggest gamma ray burster that we've ever seen, which was was a big deal last year. Now, we weren't recording at the time, otherwise we would have talked about this. I remember.
We were on a hiatus for very good reasons.
So it's October last year, GRB 221009A.
Okay, catchy name.
Yep.
And remind us, a gamma ray burster, that's one of those titles which is very descriptive without actually telling you anything about what's going on, right? Gamma rays are very high energy, very short wavelength photons. It's light, but just really high frequency light. And a burster presumably is something that bursts out a lot of gamma rays. So,
they just suddenly appear.
What is it, though? Yeah. What is it?
Well, the reason why they're called gamma ray bursters is just because we were noticing that these things just went pop with enormous amounts of gamma rays in the sky without having a clear explanation for them, at least initially, right?
Sure.
So they're called gamma ray bursters. Now, this particular gamma ray burster, there's a slight kind of variation in their origins. Most of them come from black holes, supermassive black holes eating objects.
The usual story.
Yeah.
So you trace it back and there's a black hole doing something weird. I mean, it's like quasars, right? Quasars for a long time we don't know what this is. It's just really energetic. Turns out probably supermassive black holes.
Oh, yeah. It's always supermassive black holes.
Yeah. Okay.
So in this particular event, which was about 70 times brighter than a typical gamma ray burster, we think that probably it was something like a 20 solar mass star fell into a black hole.
Oh, that's going to hurt.
Yeah.
This is last year. This is the one we're talking about last year.
Yeah.
Wow. Okay.
So, huge output of energy. We did see a tiny little optical flash as well, but we're getting most of the energy at the high, gamma rays, etc.
Right.
And so putting all that together and sort of looking at, it was bright, but it was only bright for a few minutes. So the energy output was kind of condensed into just a few minutes.
We talked about this, I can't remember when it was, which episode, but very recently talked about, what would it be like to be nearby and see it? Like, you wouldn't want to be because you wouldn't be there for very long. But imagine if you could. Imagine that, seeing like a 20 solar mass star falling into a supermassive black hole.
A huge star, right?
That would be nuts, and then you'd be dead. But that would be nuts. Anyway, so how big was that one?
So, models differ somewhat, but
there'll be error bars.
I've got a sort of numbers around 2 to 6, maybe even as much as 10. So 10 to the 54 to 10 to the 55.
Okay.
Ergs.
Okay. So again, we've moved on from biggest explosion ever that we're talking about today. We're now up to potentially 100 times, maybe sort of 10 to 100 times bigger. Getting more uncomfortable with this episode.
Yeah.
Yeah. Good.
But this is going to be reassuring for you.
Okay.
Go back to episode 61. Cast your mind back.
Well, it's well and truly gone from my memory. So you're going to have to remind me. What did we talk about?
We talked about the biggest explosion ever.
Well, yes. Yeah, we've established that. But what was it?
So basically what was found was an enormous hole in the sort of there was a big jet coming out from one of these active galactic nuclei. So again, supermassive black hole in the center of a galaxy.
Doing something weird.
Going out into the intergalactic medium, and it had carved out this enormous void.
Oh, that's right. Yeah.
Which was several times the size of the Milky Way.
Pushed all the stuff out, right?
Yeah.
And do I remember correctly that if you then work backwards and say, how much energy would it take to carve out this void through all the stuff that was there, then you come up with a very large number.
You do.
Yep.
I mean, it's a large number also because it happened over the course of a few 100 million years, right?
Sure.
It wasn't an instantaneous kaboom.
Yeah.
But it was like almost, I've got this terrible image. It's not correct, but I've got a terrible image of this giant laser just carving out this cavity.
Yeah, which I mean, sure. As opposed to an enormous bomb going off and then it's all over and then you pick up the pieces.
Yeah.
Like, this is a very, very slow bomb going off over a very, very long period of time. But it's still
with a
big
of
amount of energy.
So that's going up to 5 times 10 to the 61 ergs.
Right. That's quite a lot. I mean, I guess at some point you've got to question, are we talking about explosions here, or are we talking about systems. Like, can you even call it an event at that point? Or is it just some kind of ongoing process? At which point, surely the biggest and like the most energetic process is like the universe itself. That was the Big Bang, which is still going on now. So, at some point you kind of got to draw a line under it and say, what are we even talking about here? Are these apples and oranges?
So if you want to go by the raw numbers,
okay,
then actually the void that we talked about in episode 61, by whatever standard, perhaps you could say is still the biggest explosion ever.
Well, that's nice to know. It's nice to know that we nailed it way back in episode 61. That's good. It does still leave a question around, what are we talking about
But
today,
like you say, well, so it's processes. So, and it's actually acknowledged in some of the research itself that some of these things are very hard to distinguish. So we have talked about these AGN, active galactic nuclei, before. And a typical AGN will have a jet, and it's got some fluctuations in brightness because of the sort of stochastic feeding of the black hole. So a clump of matter falls into black hole, big energy release, clump of matter falls in. And that's not a regular thing, that's a random thing. Yeah, but it's random, but it's continually random. Yeah. So it's kind of almost like a flickering, if you like, explosion.
Sure.
Flickering feels like a too small a word, but
just a little flicker, which is going to destroy you.
Yeah, but when we come back to the system that we're talking about today, that's not ever been seen before, right? So, I mean, the authors go back at least 7 years into all the data and just say, is there any sign that this is an AGN before this event? And there's not. It's just, it's been a little quiet sort of patch of sky.
Okay, so that's weird, right? So does that imply what? That we're seeing potentially an AGN turning on?
Well, this is also an interesting thought, but it's not expected that an AGN would just sort of turn us,
Someone flicked the switch.
It doesn't feel like it works that way.
No.
So
all of this stuff surrounding this, supermassive black hole just suddenly going, hang on, we could fall into this thing, and it just starts. We hadn't thought about that before, but now we can. It's like, surely that would happen over a really long period of time.
It would be very weird for it to turn on just bang like that.
Is it possible that we just never noticed? I mean, you said that they looked back over 7 years and there was nothing. So what's going on?
Well, yeah. So the other question, so you can say, well, is it an AGN that's just sort of flickering? Probably not. We probably haven't. We would have noticed something.
Sure. Okay.
It's also extraordinarily unlikely that we would just happen to see an AGN turn on. I mean, these are not things that happen every day, right?
Sure. I mean, as you have brought up on this podcast many times before, Emily, big universe, something strange things happen all the time. And maybe one of those strange things is we just happen to be looking. But sure, let's assume that that's unlikely.
So coming back to the source of this flash, you could also say, well, hang on, didn't you just talk about that gamma ray burster?
Yeah.
That gamma ray burster was a star, big star, that fell into a supermassive black hole.
Which almost sounds careless, doesn't it? Like just wandered too close to an open manhole cover and down you go.
And so you could say, well, isn't that just an explanation? This could be a star.
Could be that.
And if you do the sums, I mean, energetically, yes, you could do that with a star. You'd have to have a star that's kind of on the order of 15-ish solar masses. But it would be, well, first of all, we think that these events where a star gets eaten by a black hole, we think these are exceptionally rare, right? Particularly when you have large stars. Smaller stars of the mass of the sun, fine, right? They're kicking around. They're in these environments, so maybe that's not such a stretch.
Sure.
But the formation of one of these stars that's this big, first of all, is incredibly rare. Even in the parts of our galaxy, of other galaxies that are forming stars like there's no tomorrow, right?
You just don't tend to get the really big ones
they're
terribly
rare.
often.
Yeah.
Like how rare?
Like really rare. I mean, you just you take 100 stars and you might form one if you're lucky.
Sure. That gives us a sense of rareness.
And that's in these very particular star-forming environments. The region around a black hole is not expected to be a great star-forming environment.
Doesn't sound great. No. So what you're saying is that, look, it's possible, but we can rule out, at least statistically, that's a very unlikely explanation. How long did that gamma ray burster last year that was the big honking star fallen into the black hole. How long did that happen over? Like what?
Just a few minutes for the burst itself and gamma rays, yeah.
As opposed to 3 years.
Yes.
So again, you're already sort of saying it's a very different mechanism.
Yes, exactly,
here.
yeah. So the timescales are very different,
Yeah.
which also points to the fact, well, maybe it's not a compact object that's just been gobbled and gone. There's probably something a bit more extended, something that's happening a little bit in this more of a general process. So that's, again, another argument for this being this giant molecular cloud. So it's quite interesting because, it's one of these papers. We've talked about them before. You start off with, here's a weird event. What could it be? Well, maybe it's this. Well, actually, this piece of evidence says, no, it's not that. Maybe it's this. Well, this piece of evidence say it's not that. And this paper does a very good job of that because we detected this particular event actually a little bit after it happened.
Right.
So it was picked up by Zwicky, the transient facility.
Mm-hmm.
So
we talked about that, last week? 2 weeks
episode.
ago?
Yeah. Which, because Zwicky's been sort of up and running for, I guess, about a year now.
And just remind us what and where the Zwicky thing is?
Zwicky is a survey telescope.
That's right.
Yeah, so it's on Palomar in California. And what they're doing is kind of just looking at the night sky and looking for transient events.
That's right, yeah.
So transient is a broad term in astronomy, but it's basically saying what's new, what's different. Is there a supernova? That will pick up things like supernova that have gone off. It will pick up things like these, this exact type of burst, light kind of object. Pick up binary star mergers. It will pick up asteroids that come too close, for example, or close enough that they sort of appear brighter suddenly in our sky.
In a very, very simple way, it's kind of like, taking a picture of the night sky, taking another picture of the night sky and eyeballing them and going, well, that bright bit wasn't there before. On a much more complex and detailed computer, machine-oriented way. It's not a human being look at it, but that's the idea.
Yeah.
What changed from this frame to this frame?
And most transient research ends up being these big, explosive kind of events.
Yeah.
Right.
Astronomical spot the difference is what we're talking about here.
Yeah. So it's not surprising that was picked up by them, but actually they picked up the rise in brightness from Zwicky, and that happened in 2021. So a couple of years ago, actually. And they were able to then go back through the data and sort of say, and back through loads of other archives of data and say, well, what was there before? And they actually noticed that the first rise in brightness happened almost a bit more than a year before that, in 2020. Yeah. It just didn't get picked up because it wasn't kind of a exciting woof of brightness. It was a very, very faint object to begin with as well. But you can go back through the data, pick it up. And indeed, it was picked up in other surveys around the same time as well. So Atlas-wise, I don't want to go into the details of those surveys, but I want to acknowledge that they contributed to them as well.
Other surveys are available.
And then if you go back further than that, in the previous 7 years, there's just Nothing.
And that's fairly conclusive.
Yeah.
We've had a really good look at this and it just wasn't something there. 2020 is when this thing started
kicking off, yeah. So then you have your 3 years, right? Because it's still 2023. But astronomers are not restricted to the optical part of the spectrum. This is an optical facility. We're saying, well, this thing's gone bright. What is it? Is it a supernova? Is it a hypernova? Is it a binary star merge? Is it just a thing that's come a bit too close to the Earth and looks like it's kind of a bit bright? Well, we know it's not that because it would have moved. But
we're ruling out all of these things.
What are the possibilities? So you do what you do, and you go and look at it with other telescopes, with other parts of the spectrum. They found it in the X-ray. So that's really exciting because X-rays are very high energy. So this was with SWIFT, the X-ray space telescope.
If you see something bright in the X-ray, you know that there's something.
There's a lot of
on.
energy. Yeah. And in fact, it's so bright that in this case, there's probably some secondary emission. So what we mean by that is that you've got clump of cloud falling into black hole, and therefore you get brightness. But that brightness has actually heated up a part of the remaining matter in the accretion disk of the black hole. So now the accretion disk is now glowing really brightly and also putting off X-rays.
Wow. So when that's getting bright enough to put off X-rays, you know that's really something going on.
Yeah, exactly. And so you can confirm that. The authors went and looked at this in ultraviolet, got some spectra. So they took the light, broke it up into its wavelengths, because when you have spectra, you can look for the temperature fingerprint of what you're looking at. You can see basically where you have peaks, and overall peak in a spectrum will tell you the temperature of an object. Just like, so we can't see things in the infrared because they're not bright enough. Well, they're not. We don't see infrared light, but what an infrared camera does is look for those photons in the infrared, and they can pick up the peaks, and you can get temperature measurements from where the peak in the infrared is. That's a very standard process that we do.
Sure. Okay.
So in this case, we're looking for the peak, and the peak turned out to be in the ultraviolet part of the spectrum.
Which is hot.
Hot, yeah. Something around maybe 13,000 degrees. And this is the emission from the disk again. So this is telling you about that secondary.
Wow.
The disk is 13,000
I mean, this
degrees.
is the equivalent of something heating up, here on Earth. And it goes through like the red hot phase, which is really hot. But then it goes through the blue hot phase, which is like, don't get anywhere near that. When you can't see it anymore, like when you can't see it glowing anymore, it's either cold or it's so hot that it's gone into the ultraviolet, and that's a concern.
Yes.
Yeah.
So very, very hot, 13,000 degrees. I mean, it's hotter than the surface of the sun.
Yeah.
Right?
Wow.
Sun's 6,000-ish. So, yeah, this is a hot disk.
Yeah,
Now,
I think everything that you're saying, Emily, is pointing towards this is big, this is hot, this is energetic.
Yeah, and then just to confirm that that's a secondary emission is coming from the disk, you can look at the infrared, and the infrared is telling us that there's loads of dust there as well. So dusty, hot, bright, supermassive black hole, cloud falling in, lots of energy.
So everything's pointing towards that is the thing. It's not a big star falling into it or being gradually ripped apart. It's this huge gas cloud. When you talk about a molecular gas cloud, is that the same thing as saying a dust cloud? Like,
yes.
Are they sort of interchangeable?
Yeah, they are a bit, yeah. So we say molecular cloud because it's got molecules in it. I mean, at 13,000 degrees, it's unlikely to have any molecules left, to be honest. Yeah. But yeah, they're kind of the same sort of thing. Dust is still there. Lots of gas, really.
Right.
Yeah.
Right.
So very exciting object. And it's at this point where I noticed in the abstract of the paper, perhaps the clue where I think maybe this could be a little bit the fault of the media that have bigged this up a bit.
Yeah, because I mean, I have seen it all over the media. I'm the one who sent you this link from, I think it was from The Guardian, saying, hey, should we talk about this one? I don't really know what it is, but what do you reckon? Because it was all over the media. I remember hearing about it on the radio. It was in the newspapers. It was all over the internet. I saw it on the social medias. Biggest explosion evs. And so what were they picking up on? Where's the hype coming in?
Here's the statement from the paper.
Yep.
This is greater than any known optical transient.
So my guess is that it all hinges on optical transient.
It absolutely does. It absolutely does.
Biggest known anything, or to get the papers, biggest known optical transient. Sorry, can you just translate that for us?
Okay. Optical.
Yep.
Optical part of the spectrum.
Sure.
So it was picked up in the optical because it was the telescopes were looking, they saw something get a bit brighter, and then they did follow-up observations with the other things. Things like gamma ray bursters, not optical transients, right?
Right.
By definition, they are gamma rays.
And hence, on your working your way up through the really big explosions scale earlier in the episode, we just swept way past this thing that we're talking about today. And the gamma ray burster was significantly larger than that by like quite a long way. But we're ignoring that because that wasn't seen in the optical. It's gamma ray. It's in the name.
Well, it's the optical transient. So the idea that there was this brightening event that we saw in the optical,
right,
rather than a brightening that we saw in gamma rays, or our episode 61 example, which was actually we just found this hole in a gas cloud
and we had to explain it.
Yeah.
Would it count if you detected it first in, say, I don't know, the X-ray or the ultraviolet, and then found that there was an optical component? Like, does that count? Does that still count as an optical transit, or is it just where you spotted it first?
That's a good question. I don't know. I know that
there must be rules about these things in the astronomical community.
Probably. Well, I think part of it is actually it's not done to be facetious, or it's not done to have a scientist.
You don't get the stamp, the big red stamp on it.
I want a medal
the
because I found the biggest whatever.
You don't get a bonus for finding. Right.
No.
Okay.
This is.
It's a shame.
Yeah, scientists are generally actually pretty level-headed.
I was being facetious, by the way. But, yeah, that makes sense.
Yeah, and they're not there to claim that I found the biggest whatever.
No.
This is not the point.
This is not what we're doing here.
The point is the physics and understanding the universe. So optical transients are actually classed in a way of slightly different phenomena to gamma ray bursters because they produce a different signature. We have seen like some probable optical counterparts, for example, to gamma ray bursters. So we've seen a gamma ray burster gone off and we've pointed some telescopes at it and we've seen, that really tiny little faint little smudge there, that's probably what it was.
Right, okay.
But that's still very different from saying, okay, that tiny little faint smudge has now just gotten, 1,000 times brighter. That's quite interesting.
Yeah. Yeah. And so if you did see that in the optical, that would be an optical transient.
Yeah.
That makes sense.
Just
sure.
and there's different physics at play that are going on with these things. Right? These bursters tend to be these short events. So they're probably more to do with these black holes gobbling stars. Maybe more of these optical transients are going to be along the lines of clouds being eaten by supermassive black holes. So let's, not be too harsh in the sense of it's certainly not the astronomers' fault.
No, I mean, your point is that it's there in the paper, right? That anyone reading this who knows what they're doing, who knows how this stuff works, who knows what the terms mean, will look at that and go, okay, so that's really big for its class, and that class being a certain range of things that can happen in the universe. But it's not everything in the universe. This is not the biggest thing that's ever happened to all things.
Well, no,
but that's kind of how the media took it.
Exactly. I mean, first of all, if you're going to talk about the biggest explosion in the universe ever, surely you'd start with the Big Bang.
Sure, yeah.
I mean, can you get any bigger than that?
I would say by definition, no.
Exactly. Yeah. So, I mean, I think you flawed from the beginning there with that one. But if you want to go with the benefit of the doubt and say since the Big Bang, I think we're starting to talk about a class of explosions, a class of events, cosmic events, which I found out today have an acronym all of their own.
Oh, go on then.
Called BOATs.
BOATs. As in BOAT.
BOAT.
Is this anything like goats?
Well,
in the sporting world, you have goats, which is the greatest of all time, which I only learned a while after actually hearing the term. People were talking about, that person is a goat. And that's really rude. Don't be nasty. Oh, I see. Greatest of all time. A boat. I'm guessing.
Today is also the first time I've heard of goats. But
can I take a stab?
Go on.
Biggest of all time?
Exactly.
BOAT? Right. And that's a thing? Like that's an actual term?
Yeah, apparently.
Okay,
I mean, if you're into these things, everyone's after the boat.
Yeah.
So what is the biggest, in this case, explosion of all time?
It does make you wonder what the goat boat would be.
Well, surely the Big
Bang.
The
Big Bang, I guess. Yeah, you really have to go back to the Big Bang being the goat boat.
Yeah. Things I never thought I'd hear myself saying. So I found a lovely paper which is all about boats, and actually it was an analysis of the gamma ray burster that we've already talked about. This 221001009A.
That one,
from last year. So there was some claims that when that one came out at the time that it could be a boat. Or that boat.
Yeah,
right. And I mean, excluding the carving out of a sort of a whole thing, which we talked about, I can see why they could make that claim, right?
But hang on. Backing up a second. Like taking the sporting analogy, right? You can talk about, for example, I don't know, tennis goats, right? Greatest of all time in tennis. Actually, you'd probably have to say, look, maybe could we compare women's tennis and men's tennis, given that they are played completely separately? Doesn't it make sense to just talk about like goats in different parts of sport? My point is, you're not going to start comparing great cricketers to great tennis players. It just doesn't make any sense.
Well, I guess somehow they have to figure out like sports person of the year, don't they?
Well, yeah, but I mean, that's probably more about sponsorship. But like in terms of greatest of all time, you can't do that. Isn't it the same here that you can't have a biggest of all time without saying biggest of all time what? Like, isn't what we're saying today that the biggest of this thing, the biggest of that thing? Because otherwise it's always the Big Bang.
Yeah, I think we all just have to agree that the Big Bang is the Big Bang.
Sure,
and since then there have been explosions in the universe, which is the biggest. And it appears to me from my very naive skim through the literature that we are talking about explosive events that happen over a short period of time.
Short.
So we're not talking about these 300 million years carving
Right.
out of holes
Okay.
in the
So we are
intergalactic
putting
medium.
a big, hazy, wobbly boundary around the word explosion-y thing here and saying it's a short asterisk period of time. Short being defined by whatever we think is right at
If
the
it
time.
looks like an explosion, it feels like an explosion. It talks like an explosion. Maybe it's an explosion.
Okay, fine, good.
So
okay.
let's say gamma ray bursters,
Sure.
right? So the gamma ray bursters are the most energetic explosions that we see in the universe today.
Fine,
So we would make sense to say, well, what's the biggest? What's the boat?
that's a boat.
Yeah.
Yep.
So there were claims that this particular one from last year would be the boat. Now, that would be extraordinary.
Mm-hmm.
You think about it. We have only been able to detect gamma ray bursters as a species for, I don't know, 50 years, maybe?
Yeah, like at most, I would have thought.
Right?
Yeah.
We've only understood the fact that we live in a galaxy and that there are other galaxies with supermassive black holes and whatnot for 100, 150 years.
But I mean, it's
We've only been extant on this earth in sort of the form of Homo sapiens for, 20, 30,000 years?
Yeah, but hang on. What are you saying here? Are you saying like are you saying we can see evidence for others in the distant past and this is bigger than that? Because I mean, I would have thought surely the whole point is it's the biggest one that we have seen. Doesn't mean it's the biggest one that has ever existed because we didn't see those.
But of all time, I think literally means of all time.
Right. Okay. So what you're saying is boat's the wrong word. Biggest of human time. Biggest one we've seen.
No. The claim is it was of all time.
But
Of
how
all
can
time.
you
The whole
compare it to
universe.
things you haven't seen? That doesn't make any sense, Emily.
Well, because
there might have been a
Chris,
really big one
Chris.
200 years ago that we didn't see.
Right. I'm gonna give you an analogy. Right.
Go on.
Right. This is a 1 in a 100-year flooding event.
Yeah.
I have this argument with my dad sometimes.
Yeah.
So his argument is, well, we don't have records that go back more than 100 years. So how do you know that it's a 1 in a 100-year flood event?
That's a fair question.
Well, you know it because of the statistics, right? You know that we might have 3 of these flooding events in 300 years, or we might have 10 of them in 10 years. And so from those statistics, although we don't have the records that go back, we can start to say, well, these events are so rare or so common in some cases that we would expect them to happen only this often.
Right. If you start, I mean, what you're saying, I think, is if you see one thing happen, if one flood happens, you have one data point. There's nothing you can do with that. You don't know if it's going to happen again next week or in 10,000 years. It's an event. But if you have a few of these events, then you can start doing some statistics on it. And preferably, the more the better. 2 is a bit difficult. 3 is even really crazy.
But you don't even need to have exact numbers of those events, right? You know more information that is more than just your singular flood, for example.
Right.
You know statistics on climate. General, Earth climate, and you can draw inferences about. We can draw inference about what the climate was 10,000 years ago.
Yes. Yeah. Okay. So you can bring in assumptions or extrapolations from what we know now and what we observe now, and the connection between that and where we are. The climate, the global atmospheric conditions and the surface conditions and so on. The equivalent in the universe is, well, we know the physics. We know what's going on. We know what happened in the past. We know what conditions were going on. And so what I'm interpreting you saying is we don't need to see loads of these things to know when we see the biggest one.
Yeah, exactly. So we know that, let's say, 20 solar mass stars, which is what we think was a part of this gamma ray burster. We know that those are exceptionally rare. We know that the chances of finding them in the vicinity of a supermassive black hole is
right. Yep.
extraordinarily rare. So we can start to build statistics, build some information about actually this is a crazy rare event.
That's an interesting idea. So the claim of a boat has to have an asterisk on it, which is statistically, I mean, this is the biggest that we have seen, but we're going to even up that claim to there hasn't been a bigger one, statistically reasoning wise, because we just would not expect that to have happened.
Exactly.
Okay.
So
I can live with that.
Coming back to my previous argument,
Yep.
We've only been observing these gamma ray bursters for 50 years. Humans have only existed for a few tens of thousands of years. Wouldn't it be
What are the odds?
Wouldn't it be weird if we just happen to effectively just turn on the instrument and suddenly we get the biggest one that's ever been in the universe? Doesn't that feel wrong?
Like for a minute I was trying to figure out, so what's the alternative? You're always going to see the biggest one that you've ever seen. But the alternative is you see a big one and you do the maths, you work out all the statistics on it, you figure out how many of that kind of environment would we expect to see on what kind of scale? And you'd go, oh, actually, we would expect to see something like that like every 20 years, which means over the last 100 years, there was probably one that was bigger than the one we just saw, right? It's that kind of thing.
Exactly.
That this is not ridiculous. It's actually pretty common. It's just the first one or the biggest one we've seen so far. But we would keep looking because we're going to see another one. As opposed to, no, we've done the maths and there's no way, well, it's not no way, but it's really, really unlikely that next year or in 10 years or 100 years, we're going to see one bigger than that.
Yeah.
And that's different.
Exactly.
And so you're right. What are the odds? That seems a bit nuts.
Yeah. So this paper sort of comes to the conclusion after a lot of analysis that actually this event that we saw last year wasn't a boat.
Okay.
In fact, it was something like a 1 in 10,000 year event.
Okay. I mean, that's still pretty rare, but the universe has been around for a really long time.
It's been around for lots of tens of thousands of years.
Yes, tens of thousands of years is a rounding error on the universe.
Yeah, it's probably not in that case.
Okay, so it's not a boat.
Yeah.
Yeah, that's a shame. It's been downgraded.
Yeah. And if we're going to be quite honest with each other, we're not going to see any boats of anything because our existence,
as per your previous reasoning,
in the universe is a flicker in the whole time period that the universe has existed. It would be astronomically improbable for us to see this.
Every time in history that humans have looked deeply into something which seemed like, wow, that suggests that we are really, really special for this thing to have happened to us. It's turned out that it's not that we're special or that we happen to look at just the right time. It's that we were going to see that anyway because it actually isn't that rare. Yeah.
I can only think of one exception, and I'll say it because, I'm going to be honest.
Go on.
I think there is one exception, and the one exception, it's not... there's a window of opportunity, which is probably on the order of a few hundred to a few thousand years. But the one thing that does blow my mind in that sense is that we live on Earth at a time when the moon and the sun are the same size in the sky.
That one still blows me away.
Yeah.
Like if you were to point at something and go, yeah, but what are the odds of that the eclipse happens to that degree? I mean, it's not precision. The moon comes closer sometimes and further away sometimes. It's like it doesn't exactly match up, but it's pretty damn close. And that is, kind of staggering coincidence.
Exactly.
It is coincidence.
I think it is because although you can...
Well, it has to be, right?
Biologists can draw conclusions about the importance of the moon for life on Earth, and maybe you need a moon on a planet for life. Maybe we needed a moon to exist.
Sure, but it didn't have to be that size.
It didn't have to be
distance.
that size and that distance and that. So I find that quite extraordinary.
Yeah. You're right. I hadn't really thought about that, but that is quite amazing. But then again, in the list of things that you could look at and go, is that a really remarkable coincidence? Is extraordinarily long. One of them had to be, right?
That's our one.
If it wasn't the moon, it was going to be something else that you go, yes, but what's the odds of this? And well, things happen.
So we don't have a boat. We've got eclipses instead. Yeah. But I'm happy with that because
that'll
they're
do.
Pretty cool.
Yeah. Everyone gets to share in that one. Right, so if we don't have a boat, we don't have a goat, we don't have a goat boat, but it's been a really fun and unexpectedly deep discussion of what it means to be the biggest And what kind of thing are we talking about? Is it an explosion? Is it something that happens over really long periods of time? Are we comparing tennis and cricket? Are we comparing apples and oranges here? I didn't expect this was going to go that way today, and I think it's been kind of fun.
I think we've even got a new meme.
Yeah?
It's going to be a supermassive black hole.
Yeah.
It's always going to be.
Who's responsible? It's the supermassive black hole. That and goats on boats, I think. I think we need to. I think the show art for this episode needs to have a goat on a boat.
So
somewhere.
now, dear listeners, next time you hear the biggest XXX or the Exiest X and the X of the universe, you can look at that with your goat boat eyes and
you
say,
know who did it. You know who's responsible. Supermassive black hole. Pull your head in. Listen, if you want to get in touch with us in order to tell us about your favourite goat or boat, doesn't really matter. We're open to either. Then there's plenty of ways that you can do that. Emily, tell us one.
So go to the Syzygy website. You got to do it. It's fabulous.
And it's the place to go. It's the place to be. It's where all the cool kids hang out.
So syzygy.fm, syzygy.fm. It doesn't even take you very long to put it into your... What do you call that bar? That bit where you put addresses in?
The thing on the browser thing.
Yeah.
The browser thing. Yeah. And once you're there, what do you find? What's on the website?
So you can find all our past episodes, which is very useful when you think, didn't we already talk about
I'm sure I've heard this, episode 61.
Yeah. You can even control F and find
yes, that's right.
nice stuff on there.
It's on there.
Yes, you can get all the past episodes and catch up and find out what we were actually talking about in that episode, because I don't think we very well represented it today.
Yeah, I'll have to go and have a listen. We'll see what we can find. But you can also find our contact page and send us through some comments and questions and anything. And you never know if it's a really good question that gets our brains working. We have been known in the past to turn listener questions into entire episodes. So try us out, see what happens. On there as well is the Great Wall of Thanks, the Cosmic Great Wall of Thanks, which is for all of the people who've supported the show, including all of our fabulous Patreon supporters. And if you want to become one of those, then you can go to patreon.com/syzygypod, where for a very small amount of money you can help keep the electrons flowing through the website and all of our social media and the live events that we do from time to time, and just help us to do the thing that we do. Otherwise, if you want to help the show, a couple of ways you can do that. Tell everyone you know. Tell that friend or relative or, favourite cousin of yours who's into nerdy space stuff to go and find us, because the more people who listen to us, the more we feel like we're doing a good job. The other thing you can do is to give us a review or a 5-star rating, and that helps us to rise up through the noise of the podcast universe. But otherwise, we're on a roll. We're doing well. We'll just keep this going. We'll be back again in a week, plus or minus a week.
Yeah, the next episode.
Yeah. Well, it's probably the best way to see it, isn't it? We'll see you at the next episode, listeners.
See you later.
Bye, everybody. So you were saying that you found something, like you went down a bit of a rabbit hole and you found another paper which had some interesting credits in it.
Yes. I'm going to have to read them to you.
Okay.
I have to go get my computer to do that.
Okay. Yep, grab it.
Yeah. So much of the last part of what we spoke about, I have to say, was inspired by a paragraph in one of the papers, the very last paper actually that I was reading before.
Yeah. So this isn't the paper. This is the rabbit hole.
This is the boat paper, which is it's a nice paper. I confess I didn't go deep into the science, but they were looking at different gamma ray bursters and looking at the claim that this one that we saw last year could be, the boat, because it was 70 times brighter than whatever. And I was reading through the conclusions because they're a useful summary. And then the second to last paragraph in the conclusions, I started reading. I'll quote now. We acknowledge the universe for timing this burst to arrive at Earth after the invention of gamma ray burst monitors, but during our active research careers. Our token optical astronomer would like to complain about the alignment with the galactic plane and requests that the next one avoid this issue. The paper is dedicated to all the unsung publications that make population analyses like these possible, particularly those that we missed.
Very nice. Very nice. Now, this does sound uncharacteristically tongue-in-cheek. You don't see this in scientific papers. You don't see people kind of making snarky aside comments and things like that. So
no, it made me do a double take. It made me look, saying, "Is this a real paper? Is this a crank paper? Is this
was this April 1st? What happened?
Yeah, where was this published? Is this what's going on?"
So this is legit. We haven't been taken for a ride.
It's absolutely a legit
here.
paper,
okay.
Because the next paragraph explains this. This paper is additionally dedicated to Dr. Alexander Khan, who unexpectedly passed away during the review of this paper. The above acknowledges are left unchanged as they were his suggestions. His expertise and input were key to this paper and many others. It is a small consolation to add this dedication in a paper that may be read in several thousand years when the fluence record is broken. I thought, I think that's really nice.
It's nice for a couple of reasons. One, because they decided to do this nice, personal, fun thing. You know, it made me smile. It's not often that you read a scientific paper that makes you actually grin. But secondly, because, you know, they did it for this colleague of theirs that died, and the publication, like the journal, left it in.
Yeah.
They didn't have to do that. They could have said, no, that's not us. We don't do that sort of thing. But they left it in. That's really nice.
And sometimes it's nice to just say what everybody's thinking, you know. I'm sure lots of astronomers, when you make claims like this is the biggest explosion the universe has ever seen, it instantly goes through the mind of everyone saying, well, isn't that fairly unlikely given the circumstances?
I hadn't thought of that. They are kind of throwing shade there, aren't they? They're kind of going, gee, thanks, universe, for doing this when we happen to be looking.
Well, exactly, yeah. And also, you know, screw you for putting it in somewhere where the optical astronomers can't get to it.
Love it. I think that's nice.
Yeah, rest in peace, Alexander Khan. You've done a fabulous job there.
That's a really nice tribute.